Hello, my Calculus 2 students or Calculus BC. This is going to be tough trying to lecture and provide you with materials and assignments and grades, but we'll get through this. We're in this together. You did an introductory video, which was a very, very, very good video on how to approximate a function using a number of terms that are polynomial. And maybe you figured it all out. Maybe you don't even need this lecture. Maybe when I give you the My Math Lab, I'm going to relook at the Khan Academy. I think you might have explored it already there too. And I'll be posting a couple assignments up for you to work through. This topic is guaranteed will be on the AP exam. I also sent you a link from the College Board. They're doing some review webinars, and you should subscribe to the channel. Download their materials. They're available when you click on the video. You'll see that it's in the comments section. Please do it. I'll be referring to some of that stuff later on. Okay? We're just going to do the best that we can. So let's get started here. We're still in infinite series, and we're talking about Taylor polynomials and their approximations. We approximate a function, and we say elementary. Elementary just means basic functions like natural log, sine, cosine. You could even do 1 over x plus 1. A lot of things you could do. And you'll find out that the approximations are pretty good, but they're only good around a certain interval. And later on, you will actually talk about the interval of convergence. You will talk about the radius of convergence, which meaning is from here to here, that would be like a radius if you had like a full circle. We're calling them both Taylor and Maclaurin. You'll see that they are talking about the same thing. It's just that where is the center? Usually your center is where you want to approximate a elementary function to be at. 0 is quite common, but you're going to see that we could shift it to other places. Then there's this little thing called the remainder of a Taylor polynomial. It usually means once you've done some terms and you have some accuracy, then everything left is the remainder till you get to infinity. Okay? That's the remainder. You approximate that. Here it goes. Now, right off the bat, the polynomial that we're creating, evaluated at some c, we would love it to be equal to f of c. But in essence, only a certain part of it will be true. The approximating polynomial is said to be expanded about c. You're expanding a polynomial around the center that you really care about. I mean, for instance, if you're on a number line and you're graphing and you care about values around 1.1, then why would you really care about accuracy over here at -10? You wouldn't. It would be so hard to create the polynomial. It might take a whole lot of terms to get accuracy to here. So we will approximate a function maybe just around the 1.1. And in reality, after this approximates, who knows what happens after that? Who knows? It could be crazy stuff. And the real function might have only been this in blue. That could have been the real function. But around this center, we can feel confident. Geometrically, the requirement that P of C equals F of C means that the graph of P passes through the point of CF of C. So for sure, we've got one solid point that is an agreement. And there's a lot of polynomials that could cross at this place. There's a lot of them. Could have been like what I wrote here, a cubic. It could have been possibly a piece of an upside down quartic. Could have been even a straight line. There's many possible answers. But see, the problem is that straight line didn't approximate as many places on the original function as I might have wanted it to. Starting out, you're tasked to find a polynomial whose graph resembles the graph of f near the point that we care about. One way to do this is to impose the additional requirement that not only does the at c you got f of c, but you also have the same slope at c. So we have cf of c, but also f prime of c is equal to the p prime of c. They're the same. That's the same. And that's the picture we have here. See, here's my elementary function. That's my elementary function. Who knows what it is? I'm looking at it and I see I'm guaranteed at c that p of c, this is my p of c, guarantees it to be here. I've also guaranteed that the slope of this curve at c is the same as the slope of my approximation. That's not very exciting. But with these two requirements, you can obtain a linear approximation. Now, linear came up in your checkup. I threw that at you. Y equals 2 is linear. Y equals 2x is linear. Y equals 2x plus 5 is also linear. So there's a lot of linear functions that we could have graphed here. That's just a line. My approximation is just a line. There's all kinds of linear. And if this slope of this curve here was 2, well then look at this. Well, except for this one. That slope's not 2. That slope is 0. But these two have a slope of 2, so they could possibly be correct as long as my function at that c is also the same as 2 times c or 2 times c plus 5. Example 1. First degree, that would mean linear. Linear is first degree. Approximation for e to the x. Now, here's my polynomial that I'm approximating. To be linear, y equals mx plus b. There's my b. There's my slope. Okay? And we are going to approximate that curve at 0. So let's just think about a linear term. If I know that f of x is e to the x, and I need f of 0 to be identical to my p of 0, then I should be able to plug in 0 into e to the x. So e to the 0 equals to 1. That's it. So right here alone, this is leading me to p of 0 also has to be 1. Now, there's no x in there, so how do I get an x? Well, let's do the derivative of e to the x. That's e to the x. Let's do the derivative of e to the x at x equals to 0. That would be e to the 0. That would also be 1. So I've got both terms that I can put together. Put this together. My p of x, which is approximately e to the x, will be approximately my 1 plus my first derivative place with the x. Basically what we're doing is plugging it into here, 1x. Now let's see how close we are. So if I'm graphing y equals e to the x, and I graph it, and I'm around 0, then around 0, I make a table. E to the 0 is 1. E to the 1 is 2.7 something. E to the negative 1 is 1 over e to the 1, which is 1 over 2.7, which has to be between 0.5 and 0.3. So if I'm graphing it by hand, it's not a surprise to realize that there is e to the x right here. Now, all I've done so far is created this polynomial with 1 plus x, which is a slope of 1 and a y-intercept of 1. So guaranteed on here, and the slope at that point is also 1. There's my polynomial that I'm using. Now, obviously, this is only good for one place, right here. That black is not even touching the red anywhere else. Well, that's life. But if I needed to use that polynomial for e to the x, you could use it for any value close to 1. You literally could take your calculator and do e to the 1.01 and compare it to 1 plus 1.01. And I would not be surprised if you get something very, very, very close, because e to the 1 is 2.7 something. This is 2.01. Okay, it's not perfect. This is closer to 3 than this one, but you only got a linear approximation. What would you need if you want to get better than that? Probably we would want maybe a quadratic approximation. And a quadratic approximation will get closer to the 2.7. Okay, let's move on. This is the solution of the author. Let's see. Yes, a sub 0 plus a sub 1. These are two different constants. There's my linear x to the 1. And when it was no x, that's really your constant term, so that doesn't really count. There's a solution, f of 0, e to the 0, f prime of 0, e to the, yep. So far, so good. And there it is. 1 plus x is approximate e to the x. There's the same picture that I had. Now, I hope you're going to talk to about the differences of these two. For each expressions about an arbitrary value of c, it's convenient to write the polynomial in this form. In other words, what if we don't know what the center is going to be? Generically, you have a constant term. You have an x to the first power term. you have an x to the second power term, you have an x to the third power term, and these constants, a sub 0, a sub 1, a sub 2, a sub 3, technically goes on forever and ever and ever until you, when you think about it, n is approaching infinity. So whatever you have a sub n x minus c to whatever power we're going to, technically. And this gets kind of confusing. I really was staring at this a little bit yesterday, and I'm not sure I can do it justice. I think the video that you watched actually was a better deal, but look what he did here. P prime means the polynomial that we start out with right here. This is P, my approximation. If you do the first derivative, the derivative of a to the 0 is 0 because it's a constant. So that's why you don't see it in here. But here, doesn't matter what this, think about what this is if you distribute it. A sub 1 times x minus a sub 1 times c. A sub 1 is just a number, c is just a number. So the derivative of all of this piece is just a sub 1. There it is. Okay, look over here, the second one here. This one, you would have to FOIL it out into x minus c times x minus c. So that looks at a sub 2 times x minus c times is x squared minus 2xc plus c squared. So now when you distribute the a sub 2, it looks like this. A sub 2x squared minus 2 a sub 2 xc plus a sub 2 times c squared. So when you do the derivative of this second term, that gives you 2 times a sub 2 times x. Where is it at? 2 times a sub 2. And where's my x minus c at? I don't have it yet. The derivative of this piece would just be minus 2 a sub 2. The derivative of this would be 0. That's a constant. So you put those two pieces together, it'll form, factor out the x minus c. You should get back to that. Try it out. If you do each term, but it's, maybe you just want to, oh no, we're doing this one, I'm sorry. Okay, let's see here. Let's try to do it. Maybe we can even do it without expanding it. That's what we can do here. I'm going to make it bigger here. P of x is a sub 0. I'm not even sure it's worth doing, but plus a sub 1 x minus c plus a sub 2 x minus c squared. I don't even know if I want to go further. Plus a sub 3 x minus c cubed, so forth. So if I'm doing the first derivative, p prime of x obviously cancels out this. This is a constant, so really think about it. What's the derivative of x minus c? A 1. 1 times a sub 1, a sub 1, plus, okay? This is just a constant. So the derivative of x minus c, using the chain rule, the 2 goes out front, 2, a sub 2, x minus c, take 1 away, times the derivative of x, which is 1, boom, plus 3 times a sub 3, 3 times a sub 3, keep the x minus c and take 1 away, squared, boom. Let's see, is it matching up? 2, did I miss something? 2 times, where's my 3a? Oh, I'm still doing the first derivative. A sub 1, 2a x minus c, 2a x minus c, plus 3a sub 3 x, yeah, there it is. So that one's doing good. All right, wonderful. Makes me so happy, all right? The second derivative of that whole polynomial, that goes to 0. This is a constant times 1, so I got 2a sub 2. The derivative of x is gone, plus 2 times 3, which is 6, 6a sub 3. Keep the x minus c to the first power. Okay, so I didn't have a whole lot of terms to begin with. But let's just see if the second derivative, yeah, there it is. We only have these two. I didn't continue. We'll talk about this mysterious end in just a second. Just for fun, third derivative of x. That's just a constant. That turns into 6a sub 3. And I got more terms. And sure enough, that's what he has. Now, how do I handle that end? Well, it's very simple here. If I go all the way to the future of, where's it at? Right here. Go all the way to the future. What's the derivative of this to get to p prime? Well, it would go, p prime of x, whatever we just did, approximately, dot, 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 dot. That power goes in the front, n, a sub n, x minus c, take 1 away, n minus 1. There it is. The next derivative, p double prime, would have taken me n minus 1 times n minus 1 times n times a sub n times x minus c, take 1 away, that becomes n minus 2. Is that what they have? There it is. There it is. There's the n times the n minus 1 times the a sub n. You got the point? One more for fun, because I know you're loving this. You're either watching this laughing, or you're sleeping, or you're not watching this at all, but you're lost because this is my only interaction I have with you. And I'd rather be there with you. N minus 2. You realize my audience is my dog and my cats, and they're staring at me. I think when I get done with this quarantine, they're going to know calculus. Maybe some of them can be hired to take your AP exam. N minus 2 times n minus 1, because you can do it at home. No one's going to know. My dog could do it for you. N minus 2, n minus 1 times the n times the a sub n times the x minus c times, take 1 away, n minus 3, boom, 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 boom. So don't forget, you got all these other terms in front. These are just the end. I did the beginning here, but then there's all these ends that we have. Purely for here. Look what was happening here. What is this? Black magic. N times n minus 1 times n minus 2. Well, that's n factorial. Whatever n you were at. This is mind-blowing. Talking to you about what's happening here. Now, if we let x equals to c, we know that p, when we say of n, I think this is standing for your whatever n I'm using here. P of n of c would have to be a sub 0, that's your first term. Your p prime, your first derivative at c, the first term gives you the a sub 1. When you do the second derivative, we were down at 2a sub 2, if you recall. And you should recall that we go to the future of n, we ended up with the n factorial. What? Where did that come from? n factorial. Well, go back to my note. All right, so that's helping you with the coefficients. And because the values of f and its first n derivatives must agree with the values of p and the first n derivative, so first derivative, the second derivative has to match to the second derivative of the polynomial and of the elementary function. The fourth derivative must match the fourth derivative of the function and the fourth derivative of the polynomial. It follows that, let me see here, what's he doing here? It follows that f of c, your function, like e to the x, will equal a to the 0. And f prime of c will equal to a sub 1. Your second derivative, though, your constant has to have divided by 2 factorial. And that's really, you're going to see this happening in a minute. And it goes on until you are dividing by whatever derivative, by whatever factorial it has. He says, he makes it sound like this is so obvious, but, it's not always that obvious. With these coefficients, you can obtain the following definition of Taylor polynomials, named after Brooke Taylor. And Maclaurin polynomials are named after the Colin Maclaurin. So how are we going to use this knowledge? Most of us don't think that hard about it. This is a Taylor polynomial with the, actually it is a Taylor polynomial because you're shifting the c. But if your c is 0, the Taylor polynomial is a Maclaurin. Okay, the Maclaurin looks easier because you're always at 0, but they're all Taylor. I mean, Taylor just means you don't have to be centered at 0. So look what we have created here. Obviously, my first term of my polynomial has to be the same as f of c. The second term came from f prime of c, had to be the same. That's how we created the first linear term of 1 plus x to be approximately e to the x. But if I need higher power, look at, to get the next term, which is my quadratic term, I need the second derivative, and it's divided by 2 factorial. You didn't notice that over here because this is divided by 0 factorial, by definition is 1. This is divided by 1 factorial, which is also 1. So the formula is consistent. If I go to the fifth derivative of c, that coefficient will be divided by 5 factorial. This is the second one, that's the fifth one. But we keep on going to the very, very, very end. It's whatever derivative you have at c divided by n factorial, x minus c to the n. If we stick around just 0, then x minus c just becomes x minus 0. So it just becomes x. So there it is, right here, if c is 0. It actually is pretty, what is he saying? Maclaurin, when you evaluate the Taylor polynomial at 0. Simple. So we got e to the x. Now we already did some of it. He wants the nth one, which isn't much fun to me because I need to see what's happening. I'm going to do a couple of them. How I tend to do this. Oops, my thing wants me to close. I don't want to close it. How would I get this up? I don't want to close it. I know it's not going to let me draw. I'm going to have to pause it and figure this out. Hold on. It won't let me pause it either. I either have to save it and get back in. Well, let me see what happens. I hope I don't have to do this all over again. Close without saving? No. Projects. Oh, I got it off. Okay. So all we start out with, my first term has to be, it's not the first derivative, it's no's derivative. Evaluated, and he says Maclaurin. So if he says Maclaurin, so we're going to go f with no derivative at 0 would be e to the 0, which is 1. To get the next term, I would have to do the first derivative, just a prime, at 0, which is e to the 0 again. But this time, it's going to have to be, oh, now this is x to the, this turns into 1x to the 0. This one has to have 1x to the 1. To do the second derivative at 0, derivative of e to the x is still e to the x. E to the 0 is still 1. That turns into a 1x to the second power. The third derivative of 0, derivative of e to the x, it's still going to be a 1, which turns into a 1x to the third. If I do f to the fourth derivative, not f to the fourth, it's the fourth derivative of x at 0, is still 1. So I'm at x to the 4, dot, 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 dot. Find the nth Maclaurin polynomial. So let me go all the way to f to the nth derivative at 0. Still a 1. And that'll turn into a 1x to the n. Now remember what my formula was. E to the x will be approximately the first term, which is 1, because 1 times 1 is 1. And there's no x's. X to the 0. This is really turned into x to the 0 times 1. So 1 plus, by the way, divided by 0 factorial, which is 1. Next term is a 1 times x, x, divided by 1 factorial. The next one was going to be a 1 times x squared, which is x squared, divided by the 2 factorial, plus x to the third divided by 3 factorial, plus x to the fourth divided by 4 factorial, plus, 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 all the way to x to the n divided by n factorial. Writing it all out, 1 plus x squared over 2, because 2 factorial is 2, plus x cubed over 3 factorial is 6, plus x to the fourth. 4 times 3 is 12. 12 times 2 is 24. Dot, 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 all the way to x to the n factorial. Not even sure if that's the answer he wanted. Mystery. Let's go to the next page and see what he has. Da, 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 da. Got it. Nailed it. Okay. That's how you do them all. I added a couple extras that he didn't have in the original. I added the sine of x. Now, I saw the video guy do it. That organic chemistry guy, he's really, really good. So, set it up the exact same way. start out with, it's still Maclaurin, so he's keeping it simple. It's at 0. So f of 0 would be sine of 0. Sine of 0, I hope you remember, is 0. F prime of 0 is the cosine of 0, which is a 1. F double prime of 0 is the derivative of cosine, which is a negative. Let me do that. Hold on. What did I just do? Hold on. It's not doing nothing. Oh, wrong button. Negative sine of 0, which is a negative 0. F triple prime of 0. So the derivative of a negative sine is a negative cosine of 0, which is a negative 1. F, the fourth derivative at 0. Derivative of cosine is negative sine, negative, negative, turns into a positive sine of 0, which is 0 again. F, fifth derivative of 0. Derivative of sine is cosine, so cosine of 0 is back to 1. And let's see. You should see a pattern. 0, 1, 0, negative 1, I think. 0, 1. Let's see if we get 0 again. F, the sixth derivative at 0. The derivative of cosine is a negative sine of 0. And that is still sine of 0. Still 0. And one more just to see the patterns working. F, the seventh derivative at 0. Derivative of sine is cosine. That's a negative cosine of 0. That is equal to cosine of 0, negative 1. So is it there? 0, 1, 0, 1, 0, negative 1. 0, 1, 0. Yep, it's working. If I go to the last one, f of n at 0, I don't really know what it is in a value because is the last one sine or cosine? And I'm doing, it doesn't make sense. So if I was putting the answer down, I would say sine of x is approximately. Obviously, I don't have a constant term. It starts, this is my x to the 0. This is my x to the 1 term. This is my x to the second. I don't have one of those. This is my x to the third. This is my x to the fourth. I don't have that. So what do you notice? I only have odd numbers. I have the 1, I have the 3, and I'm going to have an x to the 5. So I only have odd numbers. Everything else is in between. So I'm going to write it all out just so you see it. I have 0 to the x to the 0 plus, that's divided by 0 factorial. I have a 1 that goes with the x, so that's an x with the 1 factorial, plus I have a 0 with the squared, a 0 x squared over 2 factorial, plus I have a negative 1 x to the third over 3 factorial, plus I have a 0 with the x to the fourth, 0 x to the fourth, 4 factorial. I have, losing track of where I'm at, 4, I'm 5. I have a 1 with the x to the 5, plus a 1 x to the 5 over 5 factorial, plus what happened to the sixth one? May as well finish a 0 with at the sixth one, 0 x to the 6th over 6 factorial, plus, what was my next one, last one there? with the 7. It's a negative 1 right here. Negative 1 x to the 7 plus negative 1 x to the 7 over 7 factorial all the way to, all I can say is f to the nth derivative of x to the n over n factorial. Clean it up. Approximately, that's a 0. That's an x. That's a 0. That's a minus x cubed over 3 factorial. That's a 0. That's a plus x to the 5 over 5 factorial. Plus a 0. Okay, plus a 0. That would, let me change that plus 1 to be, that plus to be a minus x to the 7 over 7 factorial plus plus it was f to the nth derivative x to the n over n factorial. And feel free to do 5 factorial and whatever that is. Let's see if we're right. I don't think I have the answer there because I made this up. Guess what? Your job is to look it up and see if it's right. Obviously, you don't want to do this every single time you need an expansion for a sign. You probably will memorize the basics, just that you recognize them. When you see the cosine one, odd numbers are important. Okay, you get it? Odd numbers. And look at here. Starts positive, negative, positive, negative, positive, negative. Let's do the next. Let's see. Third degree. X minus x cubed over 6. I don't have the answer there. Cosine. Are you having fun yet? All right, so f of 0 will be the cosine of 0, and that will be, cosine of 0 is 1. That gives me 1 times x to the 0 power. First derivative, I probably won't do as many as I did the other one. Derivative of cosine is a negative sine of 0, which gives me a 0. So oh, by the way, 1 times x to the 0 will be just a 1. And 0 times x to the 1 will be 0. Second derivative at 0, derivative of a negative sign is a negative cosine of 0. Cosine of 0 is 1. That gives me the negative 1. That gives me a negative x to the 2nd power. I'm seeing something. Third derivative, 0. Derivative of cosine is negative sine. Negative, negative. Sine is a sine of 0, which is 0, which takes me to 0x cubed, which is still a 0. Last one, I think I'll prove my point. The fourth derivative of sine is cosine. Cosine of 0 is a 1. That takes me to a 1 times x to the 4th, which is equal to x to the 4th. So all the way to f to the nth derivative at 0 will be whatever it is. Okay, so cosine of x is approximately a 1 minus x squared over 2 factorial. Don't forget, this was a 0 factorial, 1 factorial, 2 factorial, which is 2. Then a 0, then a plus, a 1, x to the 4th, plus x to the fourth over 4 factorial, which is 4 times 3 times 2 times 1. So look what we got. Positive, negative, and it's evens. 2 for x to the 6th, 6 factorial, plus x to the 8th, 8 factorial, la 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 la, plus f to the nth derivative times x to the nth power over nth derivative. I don't know if I'm right or not. I haven't done these things in 14 years, so your guess is as good as mine. It's ringing a bell. You know, it was in my head somewhere, even though I wasn't using it. I think it's right. Now, don't get me wrong. As soon as I get done with this video, I'm going to do it. I'm going to go cheat and look them up and see if I'm right. But the problems, is that the sine of x? No, that's the cosine of x. Let's see. All right. Oh, my God, another one. Do I really want to do another one? No, you do it. You do it. I'll just get you started. Now, I better get you started. What happens with f of 0? What's the natural log of 0? It's undefined. So we have an issue with natural log. You aren't really going to have that term that helps you out at the 0. You might want to shift it and not do the Maclaurin, but do the Taylor and start at using the center equals to 1. Except for the fact I don't know what natural log of 1 and stuff is. Maybe don't do this one right now. Look it up and see if it makes sense. You know what? If you send it to me you make a video for me and teach me, I'll give you an extra credit grade. But I want a good video. You send me a video on what you could do with natural log of x. And I'm thinking you're going to want to do the x minus c, f to some derivative over n factorial, and so forth. Do all the terms and see what happens. It might be decimals. If you're going to use decimal numbers, then use give me 3 decimals. So I threw this in there. I didn't think ahead till I saw this error. You could still do it and write out your expansion. If you want to do c equals to 0, go ahead. Show it to me. It's okay. It's good discussion. I had. All right. Almost done here. I didn't have the answer. Remainder of a Taylor polynomial. An approximation technique is a little value without some idea of how accurate you are. You can graph them both together and see how accurate you are. I'm really amazed how a 4th degree anything gives you some pretty good numbers. To ensure the accuracy or approximate a function value, that we use the remainder. And it just tells you. Here, f of x is it's the perfect one, right? It's the function. We only did a 3rd degree, a 4th degree, or whatever. We did some polynomial of some degree, whatever it was. And you stopped. We didn't go all the way to infinity, so you have this remainder left over. This is my approximate polynomial that I'm using. It should be pretty close to this, but it's going to be off, and the part that's off is called the remainder. Check because that creates an error, obviously, if it's not perfect. So your remainder is equal to your original function minus your polynomial. Well, remember what we had. We had the function was equal to your approximation plus the remainder, which is also something of x. So if you solve this for the remainder, you got your function minus your polynomial. Now, we don't know if this remainder is positive or negative. So what we do is we take the absolute value of this. So there is the error, which is your absolute value of the remainder, will be the absolute value of f minus p. This is very fancy on the AP exam. It's called the Lagrange form of the remainder. It's actually pretty simple. I mean, the formula is really simple. The concept is very simple. Makes a lot of sense. Remember, so if you have a function, and here is obviously centered at C, so it's a Taylor polynomial. When you go all the way to that last term that we had, well, we never went to infinity. We never did. We always say you got to add a little more to get to the original function. The whole function, if I stop right here, I don't use this, I'd have to put approximately. But if you have that remainder, and let me get my remainder back again. If I have the whole thing, then I can say it's equal. Okay? And the secret to calculating the remainder, which it probably is like a part D on a problem on a free response, which since you're this year, all those multiple choice questions that we've been studying, oh my gosh, they're not going to be even on the test this year. Your remainder is always your derivative added to 1 of z. Now, because z is just this arbitrary symbol. X minus c and plus 1 because you're doing the next derivative. It's just the next term that you would use. The reason they're saying z because it's not really of x. The z just stands for the next part into the future. You're still using a function of x here. So sometimes this gets, what does that z mean? Well, you're just going to find something in terms of a z. You'll see what it does here. Let's try to work out the next one. It's been my problem. Long times I looked at it. So we've done, oh, look at this. He gave me the answer for the third Maclaurin polynomial for sine of x. Am I right? Let me go back. Yay! I love it when I remember something from 15 years ago. Use the Taylor Theorem. That's the Taylor Theorem. Taylor's theorem is when f of x equals to your approximation plus the remainder, okay? To approximate sine of 0.1 of sine of 0.1 by using your polynomial at 0.1. So recall, sine of x equals x minus x to the 3. Here's my next term over. So using his secret, there is your fourth derivative divided by 4 factorial, x to the 4th. So we would have to go to the fourth derivative and see what we get. Let's see, did he actually work it out? So I don't have to do the derivative? Well, he wrote the same thing here. Hold on here. That's the same slide. Excuse me. So let's do the derivative. We got f equals, f of x is sine of x. F prime of x equals to cosine of x. f double prime of x, which gives me this, the second degree would be negative sine of x. We got the third derivative of x to be negative cosine of x. And the fourth derivative of x, negative sine, so it'd be sine of x. So we know that we're using the sine of x and the fourth factorial. Okay, so check. That's what he had. Okay, yeah, it looks like he's going to do what? No, he hasn't done it yet. He is doing it. I saw it. I cheated. I looked x minus x cubed over 3 factorial. And we are looking for the point 1. So sine of x will be approximately the point 1 minus the point 1 cubed over 6 plus the remainder. Okay, so he hasn't done the derivative yet. There, okay, I get his paper. So these are the two terms that I had. Remember, I had it was a x. Let me go back and write out my look over here. He did this work for us, and he got 0.1 minus this decimal. I don't have my calculator handy, and if I turn on the calculator, you can't see it anyway. So I'm going to take I hope he's right, the 0.1. So the only two terms I had that took me to the third degree added up to this. This is my polynomial at 0.1. Is that. It exactly is that. Well, it's approximate because it rounded. Now, because the fourth degree is sine, which I just showed you a minute ago, we know the absolute value of the remainder at 0.1 has to be between, well, why does it have to be between 0 and this thing here? Well, because the remainder can't be 0, or you'd have a perfect polynomial. So it's bigger than 0, and it's going to have to be less than 0.0001 over 4 factorial. Well, where is that coming from? Where is that coming from? What is the sign of 0.1 for real? Because that's what that is. So I'm going to pause it. I'm going to look at my calculator. I'm just dying to see it. So I will pause. Okay, I did check it in the calculator, and I did get the sign of 0.1 to be approximately that answer. So therefore, if this answer has to be less than the sign of 0.1 plus the remainder, at 0.1, I now have my two upper bound and my lower bound. This goes 0.99833. That is less than the actual value of this one. And then this is the 8.7. Where's that at? Oh, plus the point. Add these two together. This gives you your bound of how accurate you are by only using 3 terms. Actually, 2 terms. We only use 2 terms to get the 0.098333. That was this right here. That's what we got with just 2 terms. So it's actually smaller than sine of 0.1. And this is what I got from adding the 0.0000000 to my estimation. We'll have to put together another Lagrange error problem to work on, because you could take probably an hour on those. That is the last thing here. This is probably the cloudiest part, and we'll talk about it again on part 2. We did a lot with using the Taylor polynomial expansion formula. I'll find a better problem that helps you out with this. I'm trying to think of a good reason that the remainder equals 0.0001 by 4 factor. Okay, that's by 4th term. Okay, I think I'm okay. Guys, I wish you were with me, but I'm going to load this up. It takes about a half hour for it to go to YouTube. Then I'll find an assignment for you. I'll attach to it. Bye, guys. We'll talk tomorrow.